Hello, in this lecture we'll answer two questions. In the first question, we find out the size of this angle APC is equals to x. So we have to find out the value of this angle x. And in the second question, we'll find out the length of this line segment CD is equals to x. So we have to find out the length of line segment x is equals to CD, or we have to find out the length of line segment CD is equals to x. So we start with the first question. In the drawing, we have triangle ABC. We know that BP equals to PC. So if we define the length of BP as A, then PC must be also equal to A because they are equal to each other according to what is given in the question. So PC also equals to A. In addition, we know that this is angle ABC, this is equals to 15 degrees inside. This is angle ACB, this is equals to 30 degrees inside. And again, our test is to find out the size of this angle APC is equals to x. So we have to find out the value of this angle x. So first of all, we will extend side CA, this side CA by a straight line. And then we create angle of 15 degrees at this point B in such a way that BA will be one leg of this angle equals to 50 degrees, and the other leg we create 90 degrees with the leg BA. So this angle equals to 15 degrees in its size according to our construction. In the next step, we will extend this leg by a straight line until it touches the extended side CA. And we define the touching point of the extended side CA with this extended leg. This point is point M. When doing this construction, we created the associated triangle BMC. Triangle BMC is an associated triangle because of the fact that those two angles are both equal to 30 degrees in their sizes. So here we know that BC is the base of the associated triangle MBC. So here we can implement rule 20. Repeat quickly on rule 20. According to rule 20, the perpendicular to the base of an isosceles triangle bisect the base. In the drawing, we have the associated triangle ABC. Triangle ABC is an associated triangle because side AB equals to side AC, and those circles are both equal to alpha. So triangle ABC is an associated triangle. BC is the base of this associated triangle, triangle ABC. According to this rule 20, the perpendicular from point A to the base BC, that is to say AD, bisect the base BC. That is to say, first of all, AD is perpendicular to BC, and therefore this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside according to our construction. According to this rule 20, the perpendicular AD to the base BC bisect the base BC. That is to say, it divides the base BC into two halves. The first half is BD, and it of course equals to the second half DC, and each half must be equal to BC over 2 because BC is being bisected. So in total, the perpendicular AD equals to the perpendicular AD bisect the base BC into two halves. So BD, the first half is BD equals to the second half DC, and each half equals to BC over 2. So BD equals to DC equals to BC over 2. So we can actually implement rule 20 in our drawing. In our drawing, this is the associated triangle type BMC. BC is the base of this associated triangle, triangle MBC. According to rule 20, the perpendicular from point M to the base BC bisect the base BC. That is to say, it divides the base BC into two halves. Therefore, the perpendicular from point M to the base BC must touch the base BC at point P. Why? Because of the fact that point P is the midpoint of BC. Why point P is the midpoint of BC? Because at point B, the base BC has been bisected into two halves. The first half is BP, equals to A, and the second half is PC, that also equals to A. And therefore, the perpendicular from point M to the base BC must touch the base BC at point P and not in any other point. So MP is perpendicular to the base BC, therefore this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to our construction. Repeat again, the perpendicular to the base of the associated triangle MBC, the perpendicular MP bisects the base BC. That is to say, it divides the base BC into two halves. The first half is BP, it equals to A, the second half is PC, it is also equals to A, and each half equals to BC over 2. That is 2A over 2 is of course A. Okay, so in the drawing we created here, by doing all those constructions, we created the big triangle MBC. This is the big triangle MBC. And first of all, in the right triangle MPB, this is the right triangle MPB. It's very easy to see from the drawing that in this right triangle MPB, sinus 30 degrees equals to MP over MB. Again, sinus 30 degrees in this right triangle MPB equals to MP over the opposite MB. Write it down. In the right triangle MPB, sinus 30 degrees equals to MP over MB. We define the length of the opposite MB as 2B. Again, MB equals to 2B according to our definition. So MB equals to 2B. So if you found out that in the right triangle MPB, sin square degrees equals to MP over MB. It is MP over MB. MB is 2B, so let's substitute MB by 2B. So in total, we found out that sinus 30 degrees equals to MP over 2B. Sinus 30 degrees is 1/2, so let's substitute sinus 30 degrees by 1/2. So 1/2 equals to MP over 2B. Here we multiply this equation by 2B, and we get that 2B over 2 equals to MP. We have 2 in the denominator, 2 in the denominator, so 2 will get cancelled. So in total, we found out that MP equals to B. This is the hypotenuse MP that is equals to B units in its length. So we have here the big triangle BMC. AB is the angle bisector of this triangle MBC. That is to say, AB bisect angle MBC into 2 halves. Each half equals to 15 degrees in its size. And because of the fact that MAB is the angle bisector of angle MBC in triangle MBC, we can implement here angle bisector theorem. According to angle bisector theorem, please click on angle bisector theorem. This is actually rule 19. In this triangle ABC, this is triangle ABC, AD is the angle bisector of angle BAC. That is to say, angle bisector AD bisect angle BAC into 2 halves. Each half equals to theta. So, and because of the fact that we know that AD is the angle bisector of triangle ABC, angle bisector AD divides the size of this triangle ABC proportionally. That is to say, BD over DC equals to BA over CA. Again, angle bisector DA divides the size of this triangle ABC proportionally. That is to say, BD over DC equals to BA over AC. So we can definitely implement rule 19, that is also called angle bisector theorem. In this triangle MBC, you know that because of the fact that AB is the angle bisector of angle MBC in the big triangle MBC, angle bisector AB divides the size of this big triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. And again, in triangle, the big triangle MBC, AB is the angle bisector of angle MBC. AB is the angle bisector of angle MBC in triangle MBC. Angle bisector AB bisect angle MBC into 2 halves. Each half equals to 50 degrees in its side. So we know that AB is angle bisector in triangle MBC, and therefore, according to rule 19, there's a angle bisector theorem. Angle bisector AB divides the sides of this triangle MBC proportionally. That is to say, MB over BC, only tool 19, angle bisector AB divides the sides of this triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. Open again. Because of the fact that AB is the angle bisector of angle MBC, the big triangle MBC, angle bisector AB divides the size of this triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. MB equals to 2B over BC. BC equals in total to A plus 8, that is 2A. And it is equals to MA over AC. Here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. So cancel 2. The side of the equation we left with B over A equals to MA over AC. So we found out that B over A equals to MA over AC. In other words, we can say that the right triangle MPC has been divided proportionally by line segment AP. Again, because of the fact that in the right triangle MPC, B over A equals to MA over AC, it means that the size of this right triangle MPC has been divided proportionally by line segment AP. So write it down. If you focus on this right triangle MPC, the size of, because of the fact that B over A equals to MA over AC, it means that the size of this right triangle MPC has been divided proportionally by line segment AP. So it is not. Because of the fact that B over A equals to MA over AC, it means that the sides of the right triangle MPC has been divided proportionally by line segment AP. Line segment AP divided this the size of this right triangle MPC proportionally, because B over A equals to MA over AC. And therefore, according to rule 21, that is the converse rule of angle bisector theorem, line segment AP must be the angle bisector of triangle MPC. According to rule 21, rule 21 is the converse theorem of angle bisector theorem. Converse theorem of angle bisector theorem. According to rule 21, line segment AP is the angle bisector of this angle MPC in the right triangle MPC. So I paste quickly on rule 21. According to rule 21, if we know that line segment AD divides the sides of this triangle ABC proportionally, that is to say, we know that BD over DC equals to AB over AC, then line segment AD must be the angle bisector of this triangle ABC. We only implemented rule 21 in our drawing because we know that in our drawing if you focus on this right triangle MPC, line segment AP divides the sides of this right triangle MPC proportionally. That is to say, B over A equals to MA over AC. And therefore, according to rule 21, angle AP, line segment AP is the angle bisector of angle MPC in the right triangle MPC. So, why rule 21 is the converse rule of rule 19? Because of the fact that according to rule 19, if you know that AD is the angle bisector of triangle ABC, then the angle bisector AD divides triangle ABC proportionally. That is to say, BD over DC equals to AB over AC. And rule 21 is the converse rule of this rule, rule 19. Well, according to rule 19, if we know that line segment AD divides the size of this triangle ABC proportionally, that is to say, we know that BD over DC equals to AB over AC, then line segment AD is the angle bisector of this triangle ABC. So, therefore, rule 21 is the converse rule of rule 19. So, according to rule 21, angle bisector AP bisect angle MPC. That is to say, it divides angle MPC into two halves. Angle MPC is a right angle. Therefore, the first half of angle MPC is angle MPA. That is half of 90 degrees is 45 degrees. And the second half of angle MPC, that is a right angle, is this angle X, equals to 45 degrees in size. So, in total, we found out that the size of this angle X, that is the angle that we are looking for in this question, is equal to 45 degrees in size. So, angle APC is equal to angle X is equal to 45 degrees in size. That is the answer to the first question. In the next step, I present you the second question and answer the second question of this lecture. In the second question, our task is to find out the length of side CD is equal to x. So we have to find out the length of line segment x is equal to CD, or we can say that we have to find out the length of line segment CD is equal to x. So in the drawing we have a semicircle. Point O is the center of this semicircle. This is line segment OE. This is equal to 5 units in its length. This is line segment EB. This is equal to 4 units in its length. We also know that PQ equals to CQ. PQ equals to CQ equals to QE. So those three line segments are equal to each other in their lengths. So if we define the length of PQ as A, then QE must be also equal to A, and CQ must be also equal to A because of the fact that those three line segments CQ, QP, and QE are equal to each other in their lengths according to what is given us in question. Okay, again, that our task is to find out the length of this side CD is equal to x. We have to find out the value of line segment x. We also know that those two angles are right angles. So in the next step, in the first step, we join point C and P together by straight line. By joining points P and C, we get the right triangle CPQ. We have the rule that says that in front of equal sides in the triangle there are equal angles. Okay, again, we have the rule that says that in front of equal sides in the triangle there are equal angles. So in the right triangle CPQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. We also know that the sum of the angles in a triangle is equal to 180 degrees. So the sum of the angles in this right triangle CPQ equals to 180 degrees. So which angles we have in this right triangle CPQ? Alpha plus alpha is 2 alpha plus 9 degrees. In total must be equal to 180 degrees. Right triangle CPQ, 2 alpha plus 90 degrees. In total must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Okay, again, the right triangle CPQ, the sum of the angles must be equal to 180 degrees. That is to say 2 alpha plus 90 degrees equals to 180 degrees. Here we subtract 90 degrees from this equation. We get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So here we divide this equation by 2. We get the missing angle alpha equals to 90 degrees over 2 is 45 degrees. So those two angles are both equal to alpha, and therefore each of them is equal to 45 degrees in its size. So write it down. In the next step, we join points P and D together by a straight line. It is given us the question that CE is a straight line. CE is a straight line, and according to rule 3, the sum of the angles on one side of a straight line is equal to 180 degrees. Repeat again, according to rule 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line CE at point Q? We have this angle that is the right angle, plus this plus this missing angle must be equal to 180 degrees in size according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. And therefore, triangle PQE is a right angle. In front of those two equal sides, we have those two angles that must be equal to each other in their sizes. And therefore, each angle must be equal to 45 degrees in its size. Exactly for the same reason that those two angles equals to 45 degrees in their sizes, those two angles must be also equal to 45 degrees in their sizes. Why? Because of the fact that this is a right angle that is also an isosceles triangle, and this is also a right angle that is also an isosceles triangle. In a right and isosceles triangle, we have three angles. One of them is 90 degrees, and the other one must be equal to 45 degrees in their sizes. So, in the next step, we will do a construction, that is to say, we will complete this semicircle to a circle. So we completed the semicircle to a circle, and then we will extend line segment CE by straight line until it touches the circle. And we will define the touching point of the extended line segment CE with this circle. This point is point M. Likewise, we'll extend line segment PE or side PE by straight line until it touches the circle. And we will define the touching point of the extended line segment PE with this circle. This point is point N. In the next step, we'll join point C and N together by a straight line. Likewise, we join points M and N together by a straight line. This is periangle CPN. Periangle CPN equals to 45 degrees plus 45 degrees is 90 degrees. So periangle CPN is a right angle. Periangle CPN subtend on this chord CN. Again, periangle CPN that is a right angle subtend on this chord CN. Therefore, we can implement here rule 5. Repeat quickly on rule 5. According to rule 5, any peripheral angle this equals to 90 degrees in size must subtend on the diameter of the circle. In the drawing, we have a circle. This is peripheral angle MAB, MAN. This is equals to 90 degrees in size. Peripheral angle MAN subtend on chord MN. And because of the fact that peripheral angle MAN equals to 90 degrees in size, it must subtend on the diameter of the circle. Peripheral angle MAN subtend on chord MN, and therefore chord MN must be the diameter of this circle. So according to this rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. We can implement rule 5 in our drawing. Why? Because in our drawing, this is peripheral angle CPN. This is equal to 90 degrees in size, and therefore according to rule 5, peripheral angle CPN must subtend on the diameter of the circle. Peripheral angle CPN subtend on chord CN, and therefore according to rule 5, peripheral chord CN must be the diameter of this circle. So it is known, if you found out that this is chord CN, that is the diameter of this circle according to rule 5. We have rule 7, that is the converse rule of rule 5. According to rule 7, if you know that a peripheral angle subtends on the diameter of the circle, then it must be equal to 90 degrees in size. Basically, rule 7, according to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. This is peripheral angle ACB that subtends on chord AB, that is the diameter of this circle. And therefore, peripheral angle ACB must be equal to 90 degrees in its size because it subtends on the diameter of the circle. So according to this rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. We can implement rule 7 in our drawing. Why? Because in our drawing, this is peripheral angle CMN. Actually, we join points M and then together by straight line. We join points M and then together by straight line. So this is peripheral angle CMN. Peripheral angle CMN. This is peripheral angle CMN. Peripheral angle CMN subtend on chord CN, that is the diameter of this circle. Therefore, according to rule 7, peripheral angle CMN must be equal to 90 degrees in its size. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. But this angle equals to 45 degrees, and therefore this angle must be also equal to 45 degrees in size. So in this triangle EMN, this angle equals to 90 degrees according to rule 7. This angle equals to 45 degrees, and therefore this angle must be equal to 45 degrees in size. According to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. What is the radius of this circle? The radius of this circle starts from the center of this circle, this is point O, and that's in the point on the circle itself. Therefore, the radius OB of this circle equals to OE, that is 5, plus EB, that is 4. So in total, the radius OE equals to 5 plus 4, that is 9. So the radius of this circle equals to 9 units in its length. So the radius OA equals to 9. The radius CO also equals to 9. Likewise, the radius ON also equals to 9 units in its length. In the next step, we will calculate the area of this triangle COE. Again, we calculate the area of this right triangle, triangle COE. The area of this again, triangle COE. So what is the area of this green triangle, triangle COE? Actually, we know that the area of any triangle equals to the base of the triangle times the height to the base over 2. So the area of this green triangle COE must be equal to the base of the triangle times the height over 2. We choose the base of this green triangle COE as CO. We know that CO is the radius of this circle, that is 9. So the base is CO times the height. Actually, the height must create 90 degrees if the base CO, or the height must create 90 degrees with the extended base CO. The extended base CO is Cn. Again, the extended base CO of this triangle COE is Cn. So from point A, we will draw perpendicular on Cn. So this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to our construction. We define this point as point G. EG equals to H according to our definition. So the height to the base of the triangle COE, the extended base is Cn, the height to the base is H, right? The height to the base is H because it's 90 degrees with the extended base CO, that is Cn. So the height to the base is H over 2. So in total, we found out that the area of this green triangle CO equals to the base CO times the height to the base, or the height to the extended base, that is H over 2. And again, the area of this green triangle CO equals to the base CO times the height H over 2. But CO is 9, it is the radius of this circle, so we substitute CO by 9 times H over 2. So in total, we found out that the area of the green triangle COE is equal to 9H over 2 square units in its size. And again, we found out that the area of this green triangle COE equals to 9H over 2 square units in its size. Likewise, we'll calculate the area of this lower triangle, triangle OEN. The area of this lower triangle, triangle OEN. The area of the lower triangle OEN is equal to the base of the triangle times the height over 2. And again, the area of triangle OEN, that is the area of any triangle, equals to the base of the triangle times the height over 2. We choose the base of this triangle OEN as ON. And the height is h, because it's right 90 degrees with the base ON. So the height is h over 2. So in total we found out that the area of this triangle OEN equals to ON times h over 2. So again, the area of the lower triangle OEN in total equals to the base ON times the height h over 2. ON is the radius of this angle, this is equal to 9, so let's substitute the base ON is by 9. So it is 9h over 2. Total we found out that the area of the lower triangle OEN is equal to 9h over 2 square units in size. But the area of the green triangle COE also equals to 9h over 2 square units in size, and therefore the areas of those two adjacent triangles are equal to each other. So we can write down that the area of the green triangle COE is equal to the area of the lower triangle OEN. And again, we found out that the area of the green triangle COE equals to the area of the lower triangle OEN. What is the area of this big triangle CEN? The area of this big triangle CEN this big triangle CEN. Actually, we know that the big triangle CEN, this is the big triangle CEN. The big triangle CEN consists of those two triangles, the green triangle CEO and this lower triangle OEN, and therefore the area of the big triangle CN must be equal to the area of the two components that it consists of. That is to say, it must be equal to the area of the first component, that is the area of the green triangle COE, plus the area of the second component that triangle CN consists of, that is the area of this triangle OEN. So in total, we found out that the area of this big triangle CEN, the area of the big triangle CEN equals to the area of the green triangle COE plus the area of the lower triangle OEN. So the area of the big triangle CEN is equal to the area of the green triangle COE plus the area of the lower triangle OEN. But we already found out that the area of the lower triangle OEN equals to the area of the green triangle COE. So we can substitute the area of the lower triangle OEN by the area of the green triangle COE. So in total, we found out that the area of the big triangle CEN equals to the area of triangle COE plus the area of triangle COE. That is actually 2 times the area of the green triangle COE. Here we will divide this equation by 2, and you get that the area of the green triangle COE is equal to the area of the big triangle CEN over 2. That is to say, the area of the great triangle COE is half of the area of the big triangle CEN, or the area of the big triangle CEN is twice as large as the area of the great triangle COE. So in the next step, we will calculate the area of this big triangle CEN by using the formula that the area of any triangle equals to the base of the triangle times the height over 2. So it is the area of the big triangle CEN. The area of the big triangle CEN equals to the base of the triangle times the height over 2. This is the area of any triangle, and therefore it is also the area of the big triangle, triangle CEN. We choose the base of this green triangle CEN as CE. The height to the base must create 90 degrees with the base, or we can say also that the height to the base must create 90 degrees with the extended base CE. The extended base CE is CM. Again, the extended base CE is CM. So the height to the base must create 90 degrees with the extended base CE, that is CM. We know that it is very easy to see from the domain that NM creates 90 degrees with the extended base CE, that is CM, because this is a right angle. So the height to the base is MN, because this is a right angle. Creates 90 degrees with the extended base CE, that is CM. So the height to the base is MN. Over 2. This is triangle, the small right triangle EMN. In this small right triangle EMN, those two angles are both equal to 45 degrees in their sizes, and we have the rule that says that in front of equal angles in the triangle there are equal sides. So in this right triangle EMN, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. So if we define the length of MN as B, then the length of EM must be also equal to B, because they are equal to each other according to the rule that I mentioned. So the height MN equals to B. The height MN equals to B, and the base CE, the base CE in total it is A plus 8, this is 2A. Right now, if you know that the base C of the big triangle CN is 2A, the height of the base is MN, that is B, according to our definition. Over 2. So in total, we should know that the area of the big triangle CEN is equal to 2AB over 2. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. And finally found out that the area of the big triangle CEN equals to, if 2 will get cancelled, then we have to only 8 times B. The area of the big triangle CN equals to 8 times B, square in its size. And the area of the great triangle COE equals to the area of triangle CN, that is AB, over 2. So in total, we found out that the area of the great triangle COE equals to AB over 2, square units in its size. In the next step, we will implement rule 65 in our drawing. Please click on rule 65. According to rule 65, first of all, rule 65 is true in any circle. So in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So in the drawing we have a circle. This is called AB. It intersects with this called CD at point O. Again, called AB intersects with called CD at point O. So in this drawing, the following equation is to AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement all 65 in our drawing. Why? Because in our drawing, this is called AB, the diameter of this circle, intersects with chord CM at point D. Again, chord AB intersects with chord CM at point D. So at the done, we will know that in our drawing, chord AB intersects with chord EM with chord CM at point E. The intersection point between chord AB and chord CM occurs at point E. So okay, all the requirements of all 65 are satisfied, and therefore can implement all 65 now we're going. According to all 65, the following equation is to CE times EM equals to AE times AB. And again, according to all 65, the following equation is to CE times EM equals to AE times AB. And again, according to all 65, because of the fact that chord AB intersects with chord CM at point A, the following equation is to CE times EM equals to AE times AB. CE equals to A plus A, that is 2A. EM equals to B units in itself according to our definition. EM equals to B. And is equals to AE. AE in total equals to 9 plus 5. Again, A in total equals to AO, that is 9, this is the radius of the circle, plus OE, that is 5 units according to what is given as the question. So in total, AE equals to 9 plus 5. Times EB. EB equals to 4 units in itself according to what is given as the question. EB equals to 4. So in total we should found out that 2A times B, this is 2AB, equals to 9 plus 4 is 14 times 4. So 2AB equals to 14 times 4, that is 56. We should found out that 2AB equals to 56. Here we divide this equation by 2, and finally get that AB equals to 56 over 2 is 28. AB equals to 28. We already found out that the area in the green triangle COE and the area of the green triangle COE equals to AB over 2. Repeat again. We already found out that the area of this green triangle COE equals to AB over 2 square units in its size. The area of the green triangle COE is equal to AB over 2 coordinates in size. But we just found out that AB equals to 28. So we substitute AB by 28, and we get that the area of the grand triangle COE equals to 28 over 2, that is 14. So in total we found out that the area of the grand triangle COE is equal to 14 coordinates in size. The area of this entire COE is equal to 14 coordinates in size. In the next step, we calculate the area of this grand triangle COE by using the formula that the area of any triangle is equal to the base of the triangle times the height over 2. So the area of this grand triangle COE equal to the base of the triangle times the height over 2. We choose the base of this grand triangle BOE, SOE, and the height to the base must create with the base with the extended base. The extended base of OE is ED. Again, the extended base of OE is ED. So the height to the base must create 90 degrees with the extended base. CD creates 90 degrees with the extended base ED. Therefore, CD is the height to the base of the rectangle COD. So in total, we will know that the area of the rectangle COE equals to the base OE times the height to the base CD over 2. It is given as a equation that OE equals to 5. CD equals to X. X is the line segment that we are looking for in this question. So we substitute CD by X over 2. So in total, we found out that the area of the rectangle COE is equal to 5x over 2 squared in its size. But we already found out that the rectangle COE equals to 14. So we can write down that the area of the rectangle COE equals to 14. Those two sides of the equation are equal to each other. That is to say, 5x over 2 equals to 14. Here we multiply the equation by 2 and finally get that 5x equals to 2 times 14 is 28. So 5x equals to 28. Here we divide this equation by 5 and finally get that x equals to 28 over 5 units in itself. 28 over 5 is 5.6 units in itself. So if you found out that right side CD is equals to x is equal to either 28 over 5 units in itself, or in terms of numbers is equal to 5.6 units. So again, the length of this line segment CD is equal to x, that is the length that we are looking for this question is equal to either 28 over 5 units in itself, or in terms of numbers, CD equals to x is equal to 5.6 units in itself. So we finish with the second question. The next step, the next step, we start with the repetition of the solution of the first question and then repeat on the solution of this second question. In the first question, our task was to find out the size of this angle APC. This equals to x. So we have to find out the value of this angle, angle x. So in the domain, we have triangle ABC. It's given us a question that BP equals to PC. So if we define the roof of BP as then PB must be also equal to A. You know that this is an angle ABC. This is equals to 15 degrees in size. This is angle ACB. This is equals to 30 degrees in size. Again, our task is to find out the size of this angle APC. This is equals to x. So we have to find out the value of this angle, angle x. Okay, again, we know that BP equals to PB. So if we define the roof of BP as then PB. The roof of BP is A, then PC must be also equal to A because they are equal to each other according to what is given the question. In the next step, we extended side CA of this triangle ABC by a straight line, and then we created angle of 15 degrees at point B in such a way that BA will be one leg of this angle, and the other leg creates 90 degrees with the base BA. BM creates 90 degrees with the base BA. So this angle equals to 15 degrees in its size according to our construction. The next step, we extended this leg by straight line until it touches the extended side CA, and we find the touching point of the extended this extended leg with this extended side CA. This point is point M. By doing this construction, we get that the associated triangle, triangle BMC. Triangle BMC is an associated triangle because of the fact that those two angles are equal to each other and their sizes. Each angle equals to 30 degrees. So triangle BMC is an associated triangle. BC is the base of this associated triangle, triangle BMC. Therefore, we can implement a rule 20. So repeat quickly on rule 20. According to rule 20, the perpendicular to the base of an associated triangle bisects the base. In the problem, we have the associated triangle, triangle ABC. Triangle ABC is an associated triangle because AB equals to AC. BC is the base of this associated triangle, triangle ABC. According to this rule 20, the perpendicular AD to the base BC bisects the base BC. That is to say, the perpendicular AD divides the base BC into two halves. The first half is BD, the second half is DC. The first half BD, of course, equals to the second half DC. And each half equals to BC over 2 because BC is being bisected by the perpendicular AD. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. And the first half BD equals to the second half DC, and each half equals to BC over 2. So BD equals to BC equals to BC over 2. So we can implement rule 20 in our drawing. This is the associated triangle, triangle BMC. BC is the base of this associated triangle, triangle BMC. According to rule 20, the perpendicular from point M to the base BC bisects the base BC. Because of the fact that the perpendicular from point M bisects the base BC, it means that the perpendicular divides the base BC into two halves. Therefore, the perpendicular from point M must touch the base BC at point P. Why? Because of the fact that point P is the midpoint of BC. Why point P is the midpoint of BC? Because of the fact that BP equals to PC. So the first half of BC is BP, and the second half of BC is PC. Therefore, point P is the midpoint of BC. So the perpendicular from point M to the base BC must touch the base BC at point P, not in any other point, because the perpendicular MP bisects the base BC. That is to say, the first half BP equals to A equals to the second half PC. This also equals to A. So we have here, this is the right triangle MPB. In this right triangle MPB, sum of 40 degrees equals to MP over MB. And again, this right triangle MPB, sum of 40 degrees equals to MP over MB. We define the length of the opponent MB as 2A, as 2B, of course. 2b, and b equals to 2b according to the definition. So here we have sin square degrees equals to mp over mb. mb is 2b, so substitute mb by 2b. And finally found out that sin square degrees equals to mp over 2b. Sin square degrees is 1/2, so 1/2 equals to mp over 2b. If we multiply this equation by 2b, we finally found out that mp equals to 2b over 2, that is b. mp equals to b units in its length. This is equal to mp, this equals to b units in its length. By doing all those constructions, we created the big triangle BMC. In this big triangle BMC, AB is the angle bisector of angle MBC. Again, in the big triangle MBC, AB is the angle bisector of angle MBC. Why? Because of the fact that AB divides angle MBC into 2 halves. Each half equals to 15 degrees in size. So we know that AB is the angle bisector of triangle MBC of angle MBC. And therefore we can implement the angle bisector theorem. Depend again on angle bisector theorem. According to angle bisector theorem, if AD is the angle bisector of this triangle MBC, then angle bisector AD divides the size of this triangle MBC proportionally. That is to say, BD over DC equals to AB over AC. Again, BD over DC equals to AB over this, AB over AC. Again, BD over DC equals to AB over AC. BD over DC equals to AB over AC. So we can implement rule 19 in our drawing. Because of the fact that AB is the angle bisector of angle MBC in the big triangle MBC. Angle bisector AB divides the size of this big triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. Again, according to rule 19, MB over BC equals to MA over AC. Okay, again, in the right triangle MBC, AB is the angle bisector of angle MBC, and therefore according to rule 19, angle bisector AB divides the size of the big triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. MB is 2B and BC is 2A. And again, MB is 2A, MB is 2B and BC is 2A. And it equals to MA over AC. So in total we found out that 2B over 2A equals to MA over AC. We have 2 in the denominator, 2 in the denominator, so 2 get cancelled. And we found out that B over A equals to MA over AC. Again, we found out that B over A equals to MA over AC. And therefore, if we focus on the right triangle MPC, in the right triangle MPC, line 70 AP divides the size of this right triangle MPC proportionally. That is to say, B over A equals to MA over AC. Put again, the right triangle MPC, we know that B over A equals to MA over AC. And therefore, the size of the right triangle MPC has been divided proportionally by 9/7 AP. The size of this right triangle MPC has been divided proportionally by 9/7 AP. Therefore, according to rule 21, 9/7 AP must be the angle bisector of angle MPC in the right triangle MPC. So please click on rule 21. According to rule 21, if you know that 9/7 AD divides the size of this triangle MBC proportionally, that is to say, BD over DC equals to AB over AC, then 9/7 AD is the angle bisector of this triangle ABC. Okay, so we know that 9/7 AP divides the size of this triangle MPC proportionally, that is to say B over A equals to MA over AC, and therefore line segment AP is the angle bisector of angle MPC in the right triangle MPC. So according to rule 21, AP is the angle bisector of angle MPC. Because of the fact that angle MPC is a right angle bisector AP divides the right angle into two halves. The first half is 45 degrees, and the second half is also 45 degrees. So this is angle X, angle APC equals to X, is equals to 45 degrees in size according to rule 21. So if you don't know that line segment AP is the angle bisector of angle MPC. Angle MPC is a right angle, and therefore angle bisector AP divides the right angle into two halves. The first half is 45 degrees, and the second half, the angle X, is also equals to 45 degrees in size. So in total, if you want to know that angle APC is equals to angle X is equals to 45 degrees in size. So we finished to repeat on the first question. In the next step, I'll repeat on the solution of the second question. Our test in the second question was to find out the length of this line segment CD is equals to X. Again, we have to find out the length of line segment X is equals to CD. So in the drawing, we have a semicircle. Those two angles are both right angles. We know that CQ equals to PQ equals to QE. We also know that point O is the center of this circle. Line segment OE equals to 5 units in this circle. Line segment EB, this is letter B. Line segment EB equals to 4 units in its length. Again, our test is to find out the length of this line segment CD is equals to X, or we can say that our test was to find out the length of line segment X is equals to CD. So in the first step, we join point C and P together by a straight line. By joining point C and P, we can get the right triangle CPQ. We know that in front of equal sides in the triangle, there are equal angles. Again, in front of equal sides in the triangle, there are equal angles. So in the right triangle CQP, in front of those two equal sides, we have those two angles, so they must be also equal to each other and their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha according to the rules dimension. So in the right triangle CQP, the sum of the angles must be equal to 180 degrees according to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle CQP? We have alpha plus alpha is 2 alpha plus 9 degrees. The total must be equal to 180 degrees according to the rules dimension. So in the right triangle CPQ, the sum of the angles must be equal to 180 degrees. That is to say 2 alpha plus 9 degrees equals to 180 degrees. If we subtract the 90 degrees from this equation, if I found out that 2 alpha equals to 180 degrees minus 9 degrees is 90 degrees. So 2 alpha equals to 90 degrees. You divide this equation by 2. If I found out that the missing angle alpha equals to 90 degrees over 2 is 45 degrees. Those two angles are both equal to alpha, and therefore each of them is equal to 45 degrees in its size. Likewise, we know that this is line segment CE. This is a straight line. Again, according to what is given in the equation, line segment CE is a straight line. So if you focus on the upper side of this set line C8 point Q, here the sum of the areas must be equal to 180 degrees according to all three. All three said that the sum of the areas from one side of the set line is equal to 180 degrees. So which angles we have at the upper side of the set line C8 point Q? We have this angle that is the right angle plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees and its size. So here we join points P and E together by side line. By joining points P and E, we created the right triangle PQE. In that right triangle PQE, those two sides are equal to each other. Therefore, the right triangle PQE is an associated triangle that is also a right angle. Again, triangle PQE is at the same time a right angle, is also an associated triangle. And in associated triangle, we have three angles. The first angle is right angle, the two other angles, each of them is equal to 45 degrees in size. So for those two angles are equal to 45 degrees in size. So in the next step, completed the semicircle to a circle. And then we extended side PE by side line until it touches the circle. We define the touching point of the extended side PE with this circle. This point is point M. Likewise, we extended side CE by side line until it touches the circle. We define the touching point of the extended side CE with this circle. This point is point M. The next step, we join points M and N together by side line, and we also join points N and C together by side line. This is peripheral CPN. Peripheral CPN is equal to 45 degrees plus 45 degrees is 90 degrees. Peripheral CPN equals to 90 degrees inside, and it's subtend on chord CN. Again, peripheral CPN is subtend on chord CN. And therefore, it must be equal to therefore, chord CN must be the diameter of this circle according to rule 5. So, we click on rule 5. According to rule 5, any peripheral angle is equal to 90 degrees inside, must subtend on the diameter of the circle. In the moment we have a circle, this is peripheral angle MAN, this is equal to 90 degrees inside, and therefore peripheral angle MAN must subtend on the diameter of the circle. Peripheral angle MAN subtend on chord MN, therefore chord MN must be the diameter of this circle. So according to rule 5, any peripheral angle that is equal to 90 degrees inside must subtend on the diameter of the circle. And because of the fact that this is peripheral angle CPN, is equal to 90 degrees inside, therefore peripheral angle CPN must subtend on the diameter of the circle. Peripheral angle CPN subtend on chord CN, therefore chord CN must be the diameter of the circle according to rule 5. And here you can implement the converse rule of rule 5. The converse rule of rule 5 is rule 7. Please click on rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it's equal to 90 degrees in its size. In the drawing circle, this is peripheral angle ACB that subtend on chord AB, that is the diameter of the circle, and therefore, according to this rule 7, peripheral angle ACB must be equal to 90 degrees in size. So according to rule 7, that is the converse rule of rule 5, if a peripheral angle subtend on the diameter of the circle, then it must be equal to 90 degrees in size. We can actually implement rule 7 in our drawing. Because in our drawing, this is peripheral angle CMN. Peripheral angle CMN subtend on CN, that is the diameter of the circle, and therefore peripheral angle CMN must be equal to 90 degrees in its size. So this is the right angle. Angle CMN is the right angle. In the next step, he calculated the area of this green triangle, triangle CEO. You know that the area of any triangle equals to the base of the triangle times the height over 2. Before we continue, what is the radius of this circle? the radius of any circle starts from the center of the circle, that is point O, and that's on the point that is on the circle itself. Therefore, OB is the radius of this circle. OB equals to OE, that is 5, plus EB, that is 4. 5 plus 4 is 9. So the radius of this circle equals to 9 units in itself. So we continue with the calculating the area of this triangle COE. According to the rule that the area of a triangle equals to the base of the triangle times the height over 2. The area of this triangle COE equals to, we choose the base as CO. CO is the radius of this circle, that is 9. Likewise, ON is also the radius of this circle, that is 9. So the base CO is 9 times the height. The height, once we create 90 degrees with the extended base CO. The extended base CO is Cn. Again, the extended base CO is Cn. So the height to the base must create 90 degrees with the base. So from point A we go perpendicular to the base Cn. So this angle equals to 90 degrees, and this angle also equals to 90 degrees inside, according to our construction. So EG is the height of the base CO. We defined EG as h, so EG equals to h. So in total we found out that the area of this green triangle CO equals to the base CO times the height h over 2. And again we found out that the area of the green triangle CO equals to the base CO times the height h over 2. But CO is the radius of this circle, equals to 9. So CO is 9, so in total the area of the green triangle CO equals to 9 edge over 2 squared in size. Likewise, we calculated the area of this lower triangle times OEN. According to the same formula that says that the area of any triangle equals to the base of the triangle times the height over 2. So the area of this lower triangle OEN equals to the base ON times the height edge over 2. H gets 90 degrees with the base ON, therefore it is the height. So in total we found out that the area of the lower triangle ON equals to the base times the height over 2. The base is ON, the height is edge over 2. So the area of the lower triangle ON equals to the base ON times the height over times the height edge over 2. ON is the radius of the circle, this is equals to 9. So we substitute n by 9. So this expression equals to 9 edge over 2. So she found out that the area of this lower triangle OEN also equals to 9 edge over 2 square units in size. Exactly like the area of the green triangle, this is also equals to 9 edge over 2 square units in size. So the area of the green triangle COE equals to the area of the lower triangle OEN. And again, the area of the green triangle COE equals to the area of the lower triangle OEN. The area of this green triangle COE equals to the area of this lower triangle OEN. The next step, we calculated the area of the big triangle CEN. This is the big triangle CEN. The area of the big triangle CEN must be equal to the sum of the areas of the two components that it consists of. The big triangle CN consists of, the first component is the green triangle COE, the second component is the lower triangle OEN. So the area of the big triangle CN is equal to the area of the two components that it consists of. The big triangle COE consists of, the first component is the green triangle COE, that is, so it is the area of the green triangle COE, plus the area of this triangle OEN. So in total, the area of the green triangle CN equals to the sum of the areas of the two components that it consists of. This is to say, it is the area of the first component, that is the area of the green triangle COE, plus the area of the second component, that is the area of the green triangle OEN. But we already found out that the area of the green triangle COE equals to the area of the lower triangle OEN. So we can substitute the area of the lower triangle OEN by the area of the green triangle COE, because they are equal to each other. So in total, the area of the big triangle CN equals to the area of the green triangle COE plus the area of the green triangle COE. Because we substitute the EN by the area of the green triangle COE because they are equal to each other. So in total, the area of the big triangle CN equals to the area of the green triangle COE plus the area of the green triangle COE. That is actually 2 times the area of the green triangle COE. So in total, we should find out that the area of the big triangle CN equals to 2 times the area of the green triangle COE. Repeat again. The area of this big triangle COE equals to 2 times the area of this green triangle COE. So we divided this equation by 2 and found out that the area of the green triangle COE is half the area of the big triangle CN. In the next step, we calculated the area of this big triangle CEN. According to the formula that says that the area of any triangle equals to the base of the triangle times the height over 2. We choose the base of this big triangle CEN as CE, and the height to the base must rest with the extended base CE. The extended base CE is CN. So the height to the base must rest with CM. MN can rest with CM. This is right angle. So the base of this big triangle CN is CE and the height is MN. So in total, we found out that the area of the big triangle CN equals to the base CE times the height MN over 2. CE in total equals to CQ, that is A, plus QA, that is A. So C in total equals to A plus A, that is 2A, times the height MN. MN equals to B units in the center according to our definition. Because of the fact that we know that in front of equal angles, there are equal sides. In front of those 2 equal angles, well, we have those 2 sides, they must be also equal to each other and they are. So if you define the graph of EM as B, then MN must be also equal to B according to the rule that I mentioned. So MN equals to B. The height MN equals to B. C equals to 2A and the height MN equals to B over 2. So total we found out that the area of the big triangle CN equals to 2AB over 2. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. So in total, the area of the big triangle CN equals to A times B. The area of the big triangle CN equals to A times B. And we already found out that the area of the green triangle COE equals to the area of the big triangle CN over 2. But CN is AB, so we substitute CN by AB. So the area of the green triangle COE equals to AB over 2. The area of this green triangle COE equals to AB over 2 square units in size. In the next step, we implemented Rule 65 in our drawing. Repeat quickly Rule 65. According to Rule 65, first of all, Rule 65 is drawing any circle. So this circle could be any circle. If chord AB intersects with chord CD at point O, then the following equation is true. AO times OB equals to CO times OD. So in the drawing we have a circle. This is chord AB that intersects with chord CD at point O. In this drawing, the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement Rule 65 in our drawing. This is chord AB that intersects with chord CM at point E. Again, chord AB intersects with chord CM at point E. Point E is the intersection point of chord AB with chord CM. So all the requirements of Rule 65 are satisfied, and therefore we can implement here Rule 65. And again, in our drawing, we have chord AB that intersects with chord CM at point E. Point E is the intersection point of chord AB with chord CM. And therefore, according to Rule 65, the following equation is true. CE times EM equals to AE times EB. Again, CE times EM equals to AE times EB. According to Rule 65, the following equation is true. CE times EM equals to AE times AB. CE equals to A plus A, that is 2A, times EM. EM equals to B according to our definition. Repeat again. C equals to 2A and EM equals to B. So in total, this is the equation. We have 2AB equals to AE. AE in total equals to 9 plus 5, that is 14, times AB. EB equals to 4 units in itself according to what is given as the question. So in total, we found out that to AB equals to AE is 9 plus 5, that is 14, EB is 4. So in total, 2AB equals to 14 times 4, that is 56. Again, 2AB equals to 56. If we divide this equation by 2, we found out that AB equals to 56 over 2 is 28. So she found out that AB equals to 28. But we already found out that the area of this green triangle CEO equals to AB over 2. We already found out that the area of the green triangle COE equals to AB over 2. The area of the green triangle COE equals to AB over 2. AB is 28, so substitute AB by 28 over 2. 28 over 2 is 14. So she found out that the area of this green triangle COE equals to 14 square inches in size. In the next step, we calculated the area of this green triangle COE according to the rule that says that the area of any triangle equals to the base of the triangle times the height to the base over 2. Then we found out that the area of the green triangle COE is 14 square units. So in the next step, we calculated the area of the green triangle COE according to the rule that says that the area of any triangle equals to the base of the triangle times the height over 2. Choose the base of this green triangle COE is OE, that is 5, times the height. The height to the base must create 90 degrees with the extended base. The extended base EO is ED. So the height to the base, or we can say also it is EA. So the height to the base must create 90 degrees with the extended base. The extended base is ED or EA, it doesn't matter. CD creates 90 degrees with the extended base ED. This is the right angle. So the height to the base is CD. So total we found out that the base, we choose the base of the green triangle COE is OE. The height to the base is CD over 2. OE equals to 5 units in itself according to what is given as the equation. CD is the line segment that we are looking for, this is X. So E equals to 5, CD equals to X over 2. So in total we found out that the area of this green triangle COE equals to 5X over 2 square units inside. So we already found out that the area of the green triangle COE equals to 14. So we can write down here that the area of the green triangle COE equals to 14 square inches in size. And from this equation, we derive that 5x over 2 equals to 14. Here we multiply this equation by 2 and found out that 5x equals to 2 times 14, that is 28. 5x equals to 28. Here we divided this equation by 2 and by 5 and found out that x equals to 28 over 5. In terms of numbers, it equals to 5.6 units. So AD is equals to x. It is equal to either 28 over 5 units in itself, or in terms of numbers, CD is equal to x is equal to 5.6 units in itself. Okay, thank you very much.